Okay, so we've done a whole bunch of problems that have or involve friction. Okay, and friction is a contact force, like pretty much all the other forces we've been dealing with. It is present when two surfaces are pressed together. Okay, and it's affected by basically two things. Okay? The amount of friction that you would encounter is affected by basically two things. So on your formula sheet, you have this formula. Force of friction equals mu times the normal force. Okay? Mu is the coefficient of friction. It's different depending on what two surfaces are being pressed together. Okay? You may have noticed that sometimes things don't slide past each other very easily, and other things in exactly the same situation slide past each other very easily. Okay? So the coefficient of friction is actually dependent on the two substances that are at the interface. So, for example, an interface that would have an incredibly low coefficient of friction would be ice and Teflon. Okay, which is why, if you've ever watched curling, that's what they use for the slider foot. Okay, I don't know if you ever noticed it, but they have one foot they push with and one foot that slides. Okay, the slider foot is usually a shoe that has Teflon on the bottom. So the same stuff that you would have on the frying pan. Okay, well, against ice, which also, spoiler alert, is very slippery. Okay, you put those two things together and they slide past each other very, very easily. Okay, conversely, rubber against asphalt has a very high coefficient of friction. Those two things do not slide past each other easily, which is why we use them, okay, for tires and roads. Okay? They make a good interface that doesn't result in a lot of sliding unless you do something on purpose to make them do so. Okay, everybody all right with that? So if we want to increase or decrease the amount of friction that's present, those are really the only two things that I can change. The coefficient of friction and how hard the two surfaces are pressed together. Okay, so answer me this. If I've got this desk here, what's the more logical way for me to try to move it? To push down and do this. It doesn't work very well because there's less friction between my shoes and the floor than the desk and the floor. Okay? Or to pick it up and drag it this way. Yeah, obviously pick it up and drag. Look how easy it was. Okay? I couldn't even move it the other way. Now, what did I change? Did I change the coefficient of friction or did I change the normal force? I changed the normal force. It was the same two surfaces, right? It was these funny tennis ball things they put on the bottom, okay? And the floor, okay? The surface, the coefficient of friction was the same in both situations, okay? But nobody in their right mind would try and move a desk by pushing slightly downwards and slightly forwards on it. It makes way more sense to lift it a little bit, okay? Because when I lift it, now not all of its weight is against the floor. Okay? I'm supporting part of its weight. Okay? And since if I support part of its weight, then the floor doesn't have to push back as hard, and it's easier to slide it along. Okay? Now, we do something in the wintertime to help that part of the equation in our vehicles, especially if you own a pickup truck. What do we do?
You weight down the back of the truck.
Exactly. We throw stuff in the back of the truck. Sandbags, hay bales, whatever, something heavy. I've got bags of softening salt, okay, in the back of mine because they were out of sandbags when I went to go find some. Right? So I put two 50-pound bags of softening salt in the back over my back tires. Because then there was more weight pushing down on the road, and the road has to push back more on my tires. And if you've never experienced the difference between an empty box and at least something over top of the back axle, it makes a huge difference. Okay? Even just 100 pounds makes a huge difference, okay, in the amount of traction that you have. All right? Is everyone kind of following me there? Okay. Now, we also do other things, but they more affect this part of the equation. what are some things we do that affect the coefficient of friction in the wintertime? People were just talking about it this morning. What's that?
Is that M?
It's mu, it's the Greek letter M. It looks like a U with tails.
Oh, okay. So
Yeah,
would
we
that-
can't use little m because it already stands for something.
Would that be going on ice instead of asphalt?
Okay, so I want to increase the coefficient of friction. So I'm on ice, but I want it to be less slippery.
Is that when people put like the salt and stuff down on the roads?
Okay, we can put stuff down on the roads that will aid with traction. Okay, most of that stuff, it's actually more about getting the ice to melt. Okay, when we throw sand down, sure, it does make it a little bit grippier because the sand will kind of get stuck in the ice, and then our tires grip on the rocks a little better than the ice. But the big thing with the sand and the salt is actually to lower the albedo of the snow, make it darker so it absorbs more solar energy, and put salt on it to lower its melting point. Okay, so that's actually the big reason we throw all that stuff down. It actually gets it to melt faster, in addition to a byproduct of having a little extra traction. But as you've all seen, after the first 50 cars go through the intersection where they threw the sand down, the sand's all gone, because they pushed it all to the side, or it's stuck in their tires, or whatever. And what else do we do?
What about those things you put on your shoes that have the like spikes on the bottom there?
Cleats?
Yeah.
Yeah.
No, not cleats, but like the ones so you don't slip on ice.
Yeah, it's just like a thing you wrap over top.
Yeah.
Okay, so you can get like socks, and the socks would have a lower coefficient of friction than your shoe bottom would. Okay, or you can get cleats, which will then punch into the ice, right? And that'll hold better because now it's not just about the interface here. You're getting an interface where you're redirecting the forces, right? So you're using the strength of the ice as opposed to the slipperiness of the ice by punching into it. That's why climbers will put crampons, the big spikes, on their boots when they're ice climbing. Okay. What else? Some people were talking about it this morning in this classroom. You're probably making the appointment to get them off soon.
Winter tires.
Yeah, your winter tires. Okay. Winter tires and summer tires are made of different kinds of rubber. Okay, I think we talked about this before, but the winter tires are made of softer rubber, okay, which is going to have a lower coefficient of friction. They also have the sipes in them, okay, the little cuts in the tread, okay, and that pulls water away from the interface between the tire and the ice, which prevents hydroplaning, which again increases the coefficient of friction between the tire and the ice and allows for better traction. Okay, summer tires do not have those sipes, and they're made of rubber that gets hard when it's below 5 degrees, and so they don't grip the road as well. Right? So there's things that we do, okay, in order to make traction better. To make traction better, we want FF to be bigger. Okay? Are there situations where we want FF to be smaller?
Yes.
Yeah. Okay? Those would be situations where we would lubricate things. Okay? Like in your engine of your car. You have oil in there, or at least you should. Your car won't last very long if you don't. Okay? When the oil light comes on, you should pull over and stop, because it's like, if you didn't have any blood. Okay? It's the same thing for your car if it doesn't have any oil. It's not going to go well. Okay? Yeah, oil will lubricate the metal on metal interaction that goes on inside the engine of your car, because actually metal on metal is one of the highest coefficients of friction there is. Okay, copper on copper is like the highest. Now, obviously, there's no copper in that part of your engine, but aluminum on aluminum is also pretty high. Okay, so you want to have lots of oil in there, lots of lubrication to keep those things sliding past each other easily. Okay. That sort of making sense? Okay, those two things are kind of the big part of it. Okay, so friction obviously can also lead to inefficiency. Okay? Friction is the leading cause of energy loss in most situations, because it's a force you're working against. Okay, and the more of it there is, the more energy you waste dealing with it. Okay, and it almost always produces the same 3 forms of energy when it's present: heat, sound, and light. Okay, sometimes you see sparks. Okay, or sometimes things will get so hot that they will glow. Okay, so they're not just producing heat, they're also producing light in that situation. If you've ever watched any night racing, when the cars are braking, you can actually see the rotors glow cherry red in the dark. Okay, they get so All right, snowmobiles are another one. I don't know if anyone has a snowmobile, okay? But if you don't keep going through snow and getting snow up on the moving parts of the track, okay, the track will overheat, okay, and it'll wreck the snowmobile. Okay, you can't just go over bare ice and not get anything coming up on there to melt and take away the heat energy. Okay, so you have to periodically go through the snow or a little bit of water or something like that, okay, to get those things cooled off. Okay, so this is the situation I was dealing with just a minute ago. When I tried to push that desk in the most idiotic way possible, okay, by pushing down and forwards on it, okay, I produced, okay, an applied force forwards that resulted in nothing. So what was my net force in that situation? It was 0, the desk didn't move, okay? So that applied force was going to be equal to the force of friction, okay? And by putting a slightly downward angle on it, I also added this applied force downwards, okay, which would also go along with the force of gravity also acting on the desk, and that would mean that my normal force would be the sum of these two lines going upwards, which made the friction greater. Okay, so anything we can do to reduce those two things is going to make things easier to move, right? So have you ever seen somebody dragging something along and you kind of looked at it and went, that seems dumb? It might have been, okay? They might not have been doing the things that make it easier to drag something. Okay. All right. Okay, so there's two kinds of friction. Static friction and kinetic friction. Okay? Static friction is present when the net force is 0. Okay, so that means the object's not moving. Friction is so great that the object cannot move. Okay, that's static friction. Kinetic friction happens when the two surfaces are actually sliding past each other. Kinetic meaning movement, static meaning unchanged. Okay, so when you've got kinetic friction, there's actually a sliding. Which one's always bigger?
Would you static be smaller because it net force is 0?
Everybody can't move.
Right. Well, think about this. You're pushing on something. You're pushing really, really hard. It's not moving. It's not moving. Then suddenly, all of a sudden, it gives. Once it starts to go, is it easier to push?
Yes.
Yeah. Because now you're working against kinetic friction. Once you overcome the static friction, which is always bigger, okay, you now work against kinetic friction, which is always a little bit smaller. Okay. Yeah, pushing your car. Yeah, or getting anything that's just trying to get going. If I'd have finally got that desk to move, I would have gone flat on my face, okay, because I would have been suddenly working against kinetic friction and it would have taken off on me. Okay? So yeah, kinetic friction is always a little bit smaller. Okay? Sometimes it's a lot smaller. So which one do we want if we're talking about tires and the road? Static or kinetic?
Static.
Static. Okay, so is it better to spin your tires or have grip?
Grip.
Yeah. Remember that when you're the guy trying to get out of the parking lot and you're spinning your tires like crazy. You know, the person that's on that red line, okay, on the tack, and the car is screaming and the tires are just going like this and they're trying to dig their way down through the ice to the dry pavement underneath. Okay? That's not going to work. You are trying to use kinetic friction to power yourself up the hill, when all you need to do is back off the gas, okay, and let static friction regain. That's what all traction control systems do. Okay? If your car has traction control, it's either got a limited slip differential, which is something that reduces the amount of power coming from the engine to that wheel, or it'll apply the brakes on that wheel. Depends which kind. One is better than the other, but they all have one or the other. Okay? And what it does then reduces the amount of pull on that tire to bring it back down to static friction. Okay? The same idea with anti-lock brakes. If your tires are rolling, okay, they should stop faster than if they're sliding. Okay? Because static friction is always going to be greater than kinetic. Okay? All right. Okay, let's try this one here. I'll have you guys write this one down and we'll calculate the force of static friction in this situation where I was pushing the desk at a downward angle. just a minute ago I told you got this formula on your formula sheet, and that it calculates the force of friction. We've had a ton of questions involving the force of friction thus far. Have we used that formula once? No. It's because you don't always need it to calculate the force of friction, especially in static friction cases. Because in a case where static friction is present, the net force is 0, because the object's not moving. Okay? So, in this situation then, I won't use this formula for 2 reasons. I don't know this or that, okay? And I don't really have any way to get either one of them, so yeah, that formula is pretty much out here. Okay? What I do know is that I'm pushing this way with a force of 165 newtons. Since the desk isn't moving in any direction, I know that horizontally the net force is 0, which means that the horizontal component of this 165 newtons is equal to which force? Friction, static friction in this case, okay? Because it's not moving. Okay? So I don't need that friction formula to calculate this, I just need trig. It's one calculation. Right? I find the horizontal component of that 165, and I know that the force forwards and the force resisting that force are equal. Okay? So I just have to go cos of 30 degrees times 165 newtons, and that will give me the force horizontal, which is equal to negative FF, because it would be forward and FF would be backwards. Okay? Okay, so the force of friction here is 143 newtons backwards. Okay. Very often, that's all we have to do for friction stuff is kind of a sum of all forces calculation as opposed to FF equals mu Fn. We're going to get some situations where we're using the mu part, okay, but we don't always need it.
Does that mean that the force forward is also 143?
Yeah, because that's actually what it calculated was the force forwards, and then it just made it
But it's the
backwards.
same.
Okay. Friction on an inclined plane. So let's say I set this. Did I start recording again? Good. Okay. Let's say I set this 10 kilogram block on this incline, and it doesn't move. Okay. What force is holding it there?
Friction.
Which kind?
Static.
Okay. Static friction is holding it there. Can I calculate the force of friction?
Yeah. Find
Okay.
out.
Okay. Find F parallel because the two will be
The same.
the same. Okay, so you got that part. Now, here's the next part. I'm going to give you some time to see if you can figure it out. I don't want the force of friction, although you're going to need it. I want the coefficient of friction. I want mu. Okay, you know this is a 20-degree angle. Don't forget about that internal triangle that goes here. One of the parts of it might suddenly be important that we have never cared about up until this very moment. So in this one, you're gonna need that formula. So I've got my 10 kilogram mass, okay, sitting on the plane there, so that means that this force here is going to be 98.1 newtons, as it is the force of gravity, 10 times 9.81. Okay, this side here is going to be the normal force, and in this question I'm going to need it. Okay, I have a 20-degree angle, and I know I've got F parallel. I'm also going to need that, okay, because as we pointed out earlier, the force of friction and F parallel in this situation are equal because we're dealing with a static friction situation. Okay, so let's calculate the two sides of our triangle because we know we're going to need both of those. All right, so I'm going to have F parallel be the sine of 20 times 98.1. Okay, so we're looking at 33.55 newtons. Since the net force is 0, that means the force of friction is also 33.55 newtons. This would be up ramp, okay, because this one is down ramp. All right, other force I need, normal force, okay, which is the adjacent side of this triangle, so that's going to be the cos of 20 times 98. All right, 92.18. Okay. If I want to calculate mu, what do I have to do with Fn? I'm going to divide it. Okay, so I'm going to take my force of friction and I'm going to divide it by normal force. Okay, so I'm going to have my 33.55 divided by 92.18. All right, so my coefficient of friction comes out to 0.36. I only have two significant digits. All right, now, interesting question came up a minute ago. What are my units? There aren't any. I divided newtons by newtons. They cancel. Coefficient of friction has no units. It is basically the percentage of normal force that provides friction. You're dividing the force of friction by the normal force. There are so very few situations where that number will ever be greater than 1. Okay, like I'm trying to actually think of a situation where that would happen. Okay, almost no interfaces would have a coefficient of friction greater than 1.
So the higher it is, the less friction there is.
The higher it is, the stickier it is.
Okay.
So the lower the number, the less friction, the higher the number, the more friction. Okay? All right, everybody okay with that? So now you've seen what we would use normal force for on an inclined plane, because up until now we have not touched that force. It hasn't been important, but if you get an inclined plane question and they give you mu, or they ask you to calculate it, then you're going to need the normal force on it.
So we were talking about when you're in like space and if you're going at speed, you won't stop unless something like another force stops you.
Mm-hmm.
So when you're in space and you're going like 10 meters per second, or whatever, and you're staying at that speed, your m would be 0, right?
Mu would be 0?
Would it be 0?
Yeah.
Oh,
In a vacuum, there's nothing to push on you.
okay.
Right? So air resistance is a form of friction, right? When I'm moving through the air, I push on the air pushes back. It's still friction. Okay? It's just we can reduce those forces by changing shapes and angles, which is why, like, if you look at a car from like the 80s, okay, it's built like a block. Okay? Whereas if you look at a car now, they're all shaped like a teardrop. Okay, they're much more sleek and aerodynamic because having those angles and curved edges reduces the amount the car pushes back on the air when the air hits it. It slides off of it at an angle and there's less resistance. That makes them more efficient. Okay, like I've always wondered why some semi-trucks are just flat on the front. Right? You ever seen those ones? There's just a wall. Buses, right? Yeah, like some of the school buses or even like the big tracks buses, right? They're just flat on the front. It's like, man, could you have a less efficient shape? Okay, I'm just going to push this wall through the air as fast as I can. Okay, that's basically what we're doing. So it's not super efficient. Okay, but at the same time, I've never seen a bus that's shaped like a needle, okay, on the front, which would make a lot of sense. Okay, it would be more aerodynamic to have it come down to a point. Why do you think all planes have a nose that goes to a point? Okay, you never see a plane that's flat on the front. Okay, well, actually, prop planes. Some prop planes are flatter on the front.
Wouldn't that make it easier for the bus to stop though?
Not so, I mean, your air resistance is not a force contributing a lot to your stopping, it's just contributing a lot to your inefficiency. Yes, if I had two side by side and neither one had brakes, yeah, the one that had a flat front would stop faster, if they both had to coast to a stop. All right, is that sort of making sense? Okay, here's another way that an inclined plane question could go with mu. Okay, so now we know that the coefficient of friction is 0.125, but now the box is moving. Okay, so I put that 20 kilogram box on the incline and it starts to slide. Okay, it's sliding down, but there's friction. Okay. Oh, sorry, no. I gave you the, no, sorry. Wrong situation. I'm pulling it up the ramp. Pulling the box up the ramp.
So
Okay?
is that tension?
So yes, this would be my applied force up the ramp. 120 newtons of applied force up the ramp. I want to calculate the acceleration of the box. What two forces are acting down the ramp?
Friction.
Friction and parallel force. Right. Okay, so you're going to need both of those. Okay, let's have a look at this one here, guys. So, this is our part of our free body diagram. Obviously, if we're going to get the force of friction, we're also going to need the force of gravity. We're going to need the normal force. We're going to need F parallel. Okay, all of these forces that we have to calculate in order to keep going. So, here's Fg. Okay, 20 times 9.81 is going to give me 196.2 newtons. Okay, this side here is going to be normal force. This side here is going to be F parallel. Okay, so normal force is going to be the cos of 25 degrees times 196.2. Okay, so my normal force is 177.82. I'm going to use that to get the force of friction in a minute. All right, so F parallel is going to be the sine of 25 times 196.2. Okay, 82.92. Okay, and force of friction is going to be mu times the normal force. They gave me mu, so that's going to be 0.125 times 177.82. Whoop, times, not divided. All right, so we got 22.23 newtons worth of friction. All right, so I know that this force is 22.23. I know that this force is 82.92. And I know the force up the ramp is 120. What can I calculate now? I can calculate F now. Okay, so I'm going to do vector sum of all forces. All right, so we're going to have 120 plus negative 22.23 plus negative 82.92. All right, so my net force ends up being 14.86 newtons up the ramp. Okay, because it came out positive. Can I calculate the acceleration of the box now? Okay, so F net over m, so 14.86 divided by 20. All right, so I've got an acceleration of, to two significant digits, 0.74 meters per second squared up the ramp. Okay, was that a pretty involved question? It was. I had to calculate a lot of forces on that question, for sure. And when we start getting into friction, it does get a bit like cumbersome in terms of the amount of calculating you have to do. But none of them were like really, really hard calculations. We just have to remember where everything goes.
How many points would that be on a class?
That would probably be 5 or 6. Yeah. I probably wouldn't give you marks for like calculating the force of gravity.
Oh,
Yeah, just because it's, it's easy.
that's black.
Life's not easy. I don't want to disappoint you. Sometimes it's easy, but it's not always easy.